Hello, everyone, and welcome to today's webinar, Controlling Your Organization with HashiCorp Terraform and Google Cloud Platform. Please feel free to type your questions during the webinar. We compile all questions and answers at the end of the webinar and send the results to everyone registered. This webinar is recorded, and the recording will be made available after post-processing, usually within about 2 days. With that, let's go ahead and get started.
Hi, everyone. So my name is Seth, and I'm the Director of Technical Advocacy here at HashiCorp. I've been at HashiCorp for almost 3 years, and I'm really excited to talk to you about Terraform today. As you may know, at HashiCorp, we make a number of open source tools that enable organizations to provision, secure, run, and connect any infrastructure for any application. So if you're not already using Terraform, you might recognize HashiCorp by some of our other tools seen here, like Vagrant, Packer, Surf, Consul, Vault, or Nomad. But today, we're going to be focusing on Terraform. So I know some of the people listening might already use Terraform. You might be trying it out. You might use it at large scale, and it might be a crucial piece of your infrastructure. But I also know we have other people on the line who have probably never used the tool before. So it's helpful to take a step back and talk about the goals that Terraform is trying to solve. Terraform encapsulates what we like to call infrastructure as code. It's the idea that you encapsulate all of your infrastructure dependencies and requirements in a single text file. By capturing them in a single text file, we can easily commit them to source control on something like GitHub, GitLab, Bitbucket, or Stash, and then we get things like peer review, approval workflows, and shareable components for free. Once we check that code into source control, we can easily keep a full history of all infrastructure changes. You can do that, you can do that by using something just like GitHub and tracking changes, or via something like Terraform Enterprise, which will keep track of all of your changes in your infrastructure. But then most importantly, once we capture this as code and we have a workflow around that code, we can automate everything. If it can be captured in code, it can be automated. And that's really one of Terraform's main goals. So the goal here, if we take a step back and think about infrastructure as code, the goal is to actually steal everything that application developers have had for years. So you imagine a typical application workflow, say, a Go application or a Ruby application, and those software developers, and that might be some of you on the webinar here today, you can make a pull request on GitHub or GitLab. You have your continuous integration server come along and test those changes and report right back on that code review request whether those changes are good or bad. You can have your peers come in and review that code and give you constructive feedback of whether this is a good change, a bad change, or just an okay change. From there, you can merge that code into production and have it deployed and make it in front of customers. Terraform can operate the same way, but instead of deploying applications, we're deploying infrastructure. And instead of putting something in front of a customer, we're deploying it onto a cloud provider or an external provider. And that's the goals of infrastructure as code, is really to bring everything that application developers have had for years into the infrastructure management workflow. Speaking of workflows, Terraform is designed to be one safe workflow everywhere. At HashiCorp, we make a bunch of open source tools, and that's what people know us by. But at the core, we're a workflow company. And if you've ever read the Tao of HashiCorp, you know that one of the big pillars of the Tao is workflows, not technologies. Technologies quickly evolve and change, but workflows stay forever. 20 or 30 years ago, the goals of application development and deployment were always the same. Get my code from my local laptop into production as quickly as possible. But the technologies have changed rapidly. We saw bare metal, we saw virtualization with hypervisors, we saw containerization, and we saw the proliferation of cloud providers. But the workflow has remained the same. And at HashiCorp, we're trying to provide you a workflow that's going to stay the same regardless of your underlying technology choices. It doesn't matter if you're on Google Cloud Platform or Amazon Web Services. It doesn't matter if you're using Docker, Rocket, or bare metal. Terraform provides the same safe workflow everywhere. By using a detailed dependency graph that's rooted in computer science and discrete mathematics, Terraform models relationships to adhere to ordering while maximizing parallelization. Whenever you have a large infrastructure, Terraform uses its built-in interpolation syntax to determine not only the order of operations, but the way that it can parallelize those operations most efficiently. That means even complex infrastructure, such as your entire production environment, could potentially be recreated in disaster recovery in less than 5 minutes. Additionally, because we focus on the workflow, Terraform provides a safe and reproducible workflow by separating the plan and apply phases. The plan shows a true dry run of all of the steps that Terraform is going to take before it takes them. The apply phase then executes on that plan so that you can see what changes are going to happen before you apply them. Prior to Terraform, operators and users had to try to guess what the rollout effect would be. And sometimes, for those of you that have worked with cloud providers before, what you think is an innocuous change or a simple little change can actually be very disastrous because downstream it impacts a dependency that impacts a dependency that causes a critical service to restart or go offline. Terraform manages that complexity automatically, and the plan output shows us what will happen so that we can make a decision of whether that's important or whether we should move that to a maintenance window. And then lastly, as I said before, it's one workflow. And it's not just one workflow regardless of the technology, but it's also one workflow regardless of your role. I know there are some people on the webinar here today who call themselves sysadmins, some people developers, others are operators, some people are DevOps engineers. But Terraform provides the same workflow regardless of your job role. It doesn't matter if you're a designer, a developer, an operator, or an accountant. Terraform provides the same workflow regardless of your application requirements or your job description. So I'm sure here we have lots of people deploying Python apps and Ruby apps and Java and Go, and Terraform supports all of that, again, because it's a workflow tool. And lastly, Terraform is designed to produce reproducible infrastructure. And this is one of the key things that I want to focus on for today's webinar. First, Terraform allows us to enforce parity with other environments. By using the same set of Terraform configurations, we can provision identical on-demand staging, QA, and production environments. Imagine using the same set of configurations, the same code, to produce staging and production. This means that as things are being staged, they're being staged in an environment that is nearly identical to production. Similarly, because Terraform is so fast with the parallelization and the graph, it's possible to build these environments on demand. How many people on the call today have a dedicated staging environment? I'm sure there's quite a few of you. And you probably pay for that staging environment 24/7. But I doubt that your developers work 24/7. And if they do, you should probably give them a break. So that staging environment goes unused for maybe 15 or 10 hours of the day, but you're still paying the upstream cloud provider to utilize those resources. And there are some tools out there that can turn them off and turn them back on again, but you're still paying for that utilization. And the reason that you usually don't destroy it and recreate it is that it takes too much time and it's too complex. With Terraform, it's possible to create highly ephemeral on-demand environments. That means that in, say, 5 or 10 minutes, you could have a complete replica of production ready to receive a code patch or a change, send it off to QA, and have them approve it. On the flip side, a number of people here might have staging environments that have what I like to call the deploy train. You have developers who are sitting in a queue waiting to push their changes out to the staging environment so that they can be approved by the QA department or an engineering manager or a product manager. In those situations, you have overutilized staging environment and underutilized developers. They're sitting there waiting and they're blocked while other developers are waiting for their changes to be approved. With Terraform, each developer, given the proper permission and access, could easily create their own ephemeral staging environment with their own unique URL, send that off to a QA engineer or an engineering manager, and have them approve it asynchronously. So all of these approvals and processes can happen in parallel. Because the operation is so fast, a developer can run Terraform Apply from their laptop, walk over to the water cooler or use the restroom, and come back and have a full replica of production ready to go to deploy their changes. Similarly, when they're finished, they can just destroy that infrastructure. And that means that the entire process might cost less than $1, instead of having a long-running ephemeral staging environment that costs hundreds of thousands of dollars a year. And that same process can be replicated almost anywhere. Perhaps you want to do that for QA and production. Maybe you have multiple production environments and you want to destroy them and recreate them at will. Terraform enables that. And again, it's the same set of configurations. We also have a number of customers and users who are actually using Terraform to build development environments. So they provide ephemeral development environments that are exactly like production to all of their engineers. So their engineers not only deploy code to a production-like environment, but they build their code there as well. Terraform has this notion of modules, or common configurations, that can be packaged and shared across teams and organizations. Now, if you're just a small 5 or 10 person startup, this isn't something that's going to benefit you. But as you grow as an organization, different teams and different portions of the organization have different specialties. For example, your security team might be responsible for managing all of your firewall permissions. And your networking team might be responsible for managing all of your networking and ACLs and subnets. Those two teams are likely separate. They have separate engineering managers, separate life cycles, separate agile boards that they're managing. So in a large organization, you need a way to be able to share these components between those teams. And that's what Terraform modules do. Terraform modules allow us to encapsulate a set of Terraform configurations and expose just the knobs that we want our users to be able to tune. Combined with Terraform Remote State, you can create completely independent organizations while still adhering to your organization's security practices and adhering to each team's specific requirements. And then lastly, we know that many of our customers aren't on a single cloud provider. In fact, they're not on, they're running in multiple cloud providers simultaneously. And Terraform is designed at its core to effortlessly combine high-level system providers and launch across multiple public and private clouds. So many customers are in the process of migrating from an on-premise VMware installation to a public cloud provider. And Terraform can not only help with that migration, but it can simultaneously manage both of those cloud providers. But more importantly, let's take a look at a real example. So let's talk a little bit about the multi-cloud and the hybrid cloud story. As I'm sure you know, each major public cloud provider offers their own benefits and drawbacks. Whether it's cost management, resiliency, disaster recovery, or for strict marketing purposes, many organizations are provisioning in more than one cloud to gain all of those benefits. So let's take a look at a fictitious example. Perhaps you have a really new intensive machine learning application. You want to leverage the Google Cloud TPUs that were announced just last week for the super fast processing. But you already have data on Amazon S3 for storage. And perhaps you're a Windows shop, so all of your authentication and authorization is being handled by Azure Active Directory. And then for average every day-to-day work, you're using DigitalOcean's super fast SSDs for their cost effectiveness and their high bandwidth. Now, many cloud providers have some integrated provisioning tool. Google Cloud Platform has a tool called Deployment Manager. I'm sure many of you have heard of Amazon Web Services has a tool called CloudFormation. But these tools all lack the ability to compose resources outside of the provider. They're great if you're working inside a single cloud provider, but the moment that you need to compose resources between providers, it needs to be more flexible. And that's why we designed Terraform. Additionally, there's important ordering to consider here, especially when managing these resources over time. We know that you don't just spin up infrastructure and walk away. You have to manage those infrastructure resources over months or years and keep them up and running. As changes are made and things are introduced, there's an implicit order of operations. In this example, I have to create my Azure Active Directory service before I can link any of the other services, because they rely on that authentication and authorization endpoint. Terraform automatically handles that simply by the built-in interpolation syntax. If you're coming from perhaps a Puppet background where you have to explicitly say, do X before Y, or create the folder before I create the file inside of that folder. Terraform handles that very transparently for you by using the interpolation syntax. As a user, you don't realize that there's complex graph theory under the hood that's enabling the parallelization and maximizing resource utilization. It just happens automatically. More importantly, and as I said before, Terraform focuses on a single workflow. So it doesn't matter if you're using Google, Amazon, Azure, DigitalOcean, or all four at the same time, Terraform provides the same workflow. And it doesn't matter if you're a designer, a developer, a sysadmin, a DevOps engineer, whatever your business card says, Terraform provides the same workflow for you. You put your Terraform configurations in a text file, check them into source control, and you run Terraform plan to see the changes and Terraform apply to push them out. But Terraform can manage more than just cloud providers. And I know that's something we focus on, but Terraform can manage anything with an API. Here are just a few of the over 75 integrations we have in Terraform Core. So I already mentioned Google, Amazon, Azure, and DigitalOcean. But here you can see we have DIN, which is a third-party DNS provider for top-level DNS resolution. Kubernetes, which is a tool for managing applications and application scheduler. Chef, which is a configuration management tool. Additionally, we have plugins and integrations for all of the other HashiCorp tools, Consul, Nomad, Vault, and Terraform. You can easily query secrets from Vault, read and write data from Consul's key value store, or schedule applications with Nomad. And Terraform can actually consume other Terraform configurations via the Terraform remote state resource and the Terraform data sources. And then thinking outside of the infrastructure management box, we have integration with tools like New Relic and Heroku, where you can quickly deploy applications and monitor them. And then one of my personal favorites is our GitHub integration. Now, GitHub seems a little bit out of left field. We're talking about infrastructure and DNS and monitoring, and how does GitHub fit into that picture? Well, you can actually use GitHub and Terraform to provision all of your repositories and permissions between them. So instead of going in the GitHub UI and clicking and adding people to teams and giving teams repository permissions, and some people get read access and some people get write access, you can actually codify or put that in code in Terraform and then have Terraform manage all of that for you. So imagine a workflow where a new user joins your company, a new employee, a new engineer, and their very first job is to go into this Terraform configuration and submit a pull request to add themselves to the teams that they're going to be contributing to. The next time Terraform runs, they automatically gain all of the permissions that they need to push, pull, or update any of those repositories. And this isn't just a hypothetical example. This is a real thing that real organizations are doing. And you can read more about it on the HashiCorp blog. I wrote a very detailed blog post about how you might do this. You can control everything from users to repositories, all the way down to labels and colors across your organization. Another thing I want to highlight here is Google Cloud. Now, I know Google Cloud is just a cloud provider, but they're actually a lot more than that. Google Cloud provides a number of high-level isolation components, including organizations, projects, and folders. Even though you're using the same login with the same web interface, Google Cloud allows you to segregate resources at the organization layer via folders or via projects. And you can think of these as individual subjugated areas of Google Cloud that, unless given explicit permission, cannot break outside of their project. And this is very useful for large organizations that want to do things like roll-up billing, where you want to bill each individual organization separately, but you only want to write one check to Google Cloud. It's also great for things like training environments. Excuse me. Imagine a situation where you need to give a user a VM that has pre-installed software on it. They should have full unrestricted access to the internet, but they shouldn't be able to talk to other people in the training environment. But as an instructor, I want to be able to see all of the virtual training VMs, and I want to be able to go in and assist an attendee if they get lost. And this is actually a demo I'm going to give at the end of this presentation. It's a very real-life use case that Google Cloud Platform isolation layers help us solve. So as you can see, as I said before, there's over 75 integrations, and to support this broad range of integrations, Terraform has an amazing ecosystem. This is Terraform's GitHub pulse as of last week. As you can see, Terraform is a very vibrant project with many committers, issues, pull requests, and both internal and external committers. So in this page here, this is over the past 7 days, you can see we had 36 unique contributors pushing 150 commits to master with 280 commits across all branches. There were 242 files changed and almost 8,500 total additions of code. More importantly, we see that there were 83 merged pull requests and 61 closed issues. To support that workload, we have over 1,000 unique contributors, and 8 of them are full-time HashiCorp employees. So their full-time job is to work on Terraform, Terraform providers, Terraform core, issue triage, pull request, and keeping community engagement up and running. On top of that, we have 1.5 full-time Google engineers who are dedicated to the GCP provider. At HashiCorp, we officially support the Google provider, AWS, Azure, Oracle Public Cloud, and Terraform Console Vault and Nomad. We are very fortunate today to be joined by one of those 1.5 full-time employees at Google, Dana Hoffman. I'm going to hand it over to Dana here to talk about her role at Google, but be sure to stick around to the end because there will be a live demo. So Dana, take it away.
Hi everybody, my name is Dana Hoffman and I am a software engineer on Google Cloud Platform. I'm really excited to talk to you all today about how to use Terraform to set up your GCP organization in a way that's simple and repeatable, and maybe also teach you something about Google Cloud Platform that you didn't already know. So before we dive into actually how to manage your Google Cloud organization, I want to talk a little about what Google Cloud Platform, or GCP, is and what it offers for those of you that may not be as familiar. So what is Google Cloud Platform anyway? Well, Google Cloud Platform is Google's offering into the public cloud space. It lets people run their applications and workflows on the same infrastructure used to power Google and get all of the benefits that come with that. Here are 3 examples of our product offerings that I think are really great. So first up is our compute and networking offerings. Within compute, we offer Compute Engine, which is a way to customize your VM experience, Container Engine, our Kubernetes-based platform for containers, and App Engine, our fully managed application development platform. Our compute VMs offer live migration, so they don't have to be rebooted for host software updates or operational tasks, which gives them incredible uptime. We also offer auto-scaling with managed instance groups, and these can automatically add and remove instances based on load. We offer per-minute billing and sustained use discounts, so you're truly paying for what you actually use. Speaking of which, we offer customizable machine types, so you can configure the right combination of memory and CPU for your workload. Lastly, we offer global networking and global load balancing, which easily scales to millions of requests per second and tolerates extreme spikes in traffic. Within storage, we have several different SQL and NoSQL options, from our managed Cloud SQL to our blob storage option, Cloud Storage, to the newly released Cloud Spanner, among others. Cloud Spanner is especially exciting because you get strong consistency guarantees, as well as horizontal scalability to hundreds or even thousands of servers. I've gotten a chance to use Spanner for some work that I've previously done at Google, and so I'm super excited that we're releasing this for the rest of the world. The last part of Google Cloud I want to talk about right now are big data services. We have BigQuery, our analytics platform, which is both insanely fast and easy to use. It's serverless and the syntax is SQL-based, so you don't have to learn anything new or have to worry about setting it up correctly. You just import your data and run whatever analytics you want to. For processing, we have Dataflow, which supports streaming and batch execution of pipelines, and Dataproc, our managed Spark and Hadoop service. We also have machine learning services with APIs for vision, speech, natural language, and more, and Cloud Machine Learning Engine, which is our managed TensorFlow service. So even though these are just 3 of the many things the Google Cloud Platform offers, I wanted to make sure that you all got a chance to hear about them from somebody that works at Google and has used some of these before I joined the cloud team and before I started working within open source. So at Google Cloud Platform, we have a strong commitment to open source, both through our own open source libraries like Kubernetes and TensorFlow, but also through our partnerships with companies making great open source tools. So it should be no surprise how much we value our partnership with HashiCorp. If we can give developers who use HashiCorp tools to manage their cloud infrastructure a really, really great experience, then the better experience they'll have with GCP as a whole. Because of that, we have full-time engineers from Google, such as myself, whose job it is to work on HashiCorp products full-time. So even though I'm a Google employee, the vast majority of the code that I'm currently writing is for Terraform. In addition to our dedicated staff, we also have what we call 20%ers. These are employees on other teams who spend up to 20% of their working time working with our team on projects like Terraform and other HashiCorp products. And so earlier this year, we wanted to showcase this partnership. So we made a 4-part video series, which uses an example of a game studio looking to create an online multiplayer game to showcase how to use Vagrant, Packer, and Terraform, along with GCP, to create, deploy, and scale our demo game. Links to these 2 blog posts that you can see here in the slides will be sent out after the webinar, or you can also search for Google and HashiCorp mini-series if you prefer to find them right now. And if you're curious what I look like, I'm in the Terraform video. Haha. So next, I'm going to dive into the GCP resource hierarchy. So the cloud resource hierarchy allows your company to map its organizational structure onto GCP. It has 3 main components: organization, folders, and projects, plus the resources those projects own. I want to point out that there are no users in this diagram. GCP is project-based, and any step on the hierarchy can have access controls on it to limit access to a set of users or Google groups. At the top of this diagram is the organization. This is essentially your company. So for example, I'm a part of the google.com organization. G Suite and Cloud Identity customers automatically have an organization resource. It's still possible to use GCP without an organization, so if you're just playing around for personal use, you can still do almost everything that we're going to be talking about today. We'll just be a little bit more limited in some of this organizational structure that I'm talking about right now. Once an organization resource is created, all GCP projects in that domain will be part of that organization by default. This means projects can be centrally managed by an organization admin, and also you don't have to worry about what happens when an employee leaves the company. They will lose access to the project that they were in, but the project will still stick around, and everybody else that had access to it still will. You can also grant IAM roles at the organization level. These roles are then inherited by all folders and projects under the organization. So for example, let's say you have a networking team in your organization. Instead of having to grant them the network admin role for every single project within the entire organization, you can grant the team the role at the organization level, which allows them to manage all of the networks and all of the projects in the whole company. Next up are folders, which provide an additional grouping mechanism and isolation boundaries between projects. Folders can contain projects or subfolders, so you can easily model your department hierarchy. Like we saw in organizations, IAM roles granted on a folder are automatically inherited by all projects and folders within that folder. After that are projects, which are the core organizational component of GCP. All resources must belong to exactly one project. Projects form the basis for creating, enabling, and using all cloud platform services, managing APIs, enabling billing, adding and removing collaborators, and managing permissions. Last up are resources. This diagram shows compute engine instances, app engine services, and cloud storage buckets as possible resources, but that's far from a complete list. Except for the more meta Terraform resources like project or IAM policy or service account, Terraform resources and Google resources are essentially equivalent. Terraform currently has resources available within Compute Engine, Container Engine, BigQuery, Cloud DNS, Cloud SQL, Cloud Storage, and PubSub, with more to come soon. A resource is one small piece of infrastructure that you can manage, such as a Compute Engine network or a GKE cluster. So now that you know what an organization is and what a project is and what it means for your organization, I want to give a quick overview of how to actually use Terraform to create a new project. After the diagram, it might seem a bit daunting, but it's actually incredibly simple. To start, you'll need your organization ID, and if you want to enable billing on the new project, your billing account ID. For the sake of time and your own interest, I'm not going to go over how to find that information now, but there are instructions on cloud.google.com if you don't already know, and you could easily Google for help as well. With that information, creating a new project in GCP takes just a few lines of Terraform code. In this sample, we've created a Google project resource with a project ID and name. We've tied this to our organization and given it a billing account. Note that in the moment, the folders API is still in beta, so we've created our project directly in the organization, which you could do regardless of folders being in beta or not. However, we're looking forward to seeing folders launch, so we can start adding support for them in Terraform too. So that was just an example for one single project. Next, I'll walk through a slightly more complicated example, setting up a project for new developers to an organization. This is very similar to the demo that Seth mentioned, but make sure to stick around because his is going to be a live demo and mine is just a couple of slides to show a little bit in depth of what you can do. So let's say you're an organization administrator and you want to set up a new project for every new developer that joins your organization. For now, we'll say the only requirement is that it needs a virtual machine that you can SSH into, but you can easily imagine other setup that you might want. For example, Google storage buckets with pre-populated data. Maybe that VM has a custom image on it with pre-installed software. Maybe there's a managed instance group that actually already has a demo version of the app that you develop. This could be anything, but for the sake of keeping it short for the slides, it's just going to be a single VM with SSH access. So all of this could be done in the Cloud Console. You don't have to use Terraform ever, but it requires a lot of clicking around and waiting in between actions. And so the Cloud Console is really great when you're just trying things out for the first time. You're not really sure what to do. You can see all of your options right there. It has a really great UI. But if you want to scale it, do something multiple times, it can be a bit slow, and I'll show you what it would end up looking like. So the first thing you would do is create the project, and then you have to wait for it to finish creating before you can do anything else. Next up, we'd switch to that project and then enable the Compute Engine API so we can actually create our VMs. Then we need to wait for it to enable before we can do the next step. After that, we can actually create the instance. Fill out the form, and the instance is created. Now, this was a contrived, simple situation, so it would only be a few minutes of work. And of course, it was just a few seconds of work right now, but I've shown you screenshots instead of actually clicking through and waiting for pages to load. But what if we needed to do even more setup for our new user? So some of the other examples that I came up with earlier, or maybe some that you've come up with yourself while listening. What if we have more than a few users that need the same configuration? What if it's, 5 or 10 or 100? We don't necessarily want to have to click through this 100 times. What if we want to be able to go back and make changes to these configurations later? So all of these different compute options, what if there is something that we wanted to change and we wanted to apply across the board? As the amount of work increases, the time that it would take to use the Cloud Console to do this work would go up similarly. And with it already taking a few minutes for a simple configuration like this, we want a more automatable solution. So here's how we would do it in Terraform. The first thing we do is set up our Google provider with a region that we specify and a path to our credentials. If you're not sure where these credentials come from, there's documentation on the Google provider page at terraform.io that explains how to get credentials for their default compute engine service account, or you can create a custom service account that you use with Terraform. After we've set up our provider, we create the project. And so in this one, we've called our resource demo, and the project ID is tfdemo, and then whatever our user is, because we are assuming that we are setting up this project for a particular user. So we've put their name in the project ID. And we've passed in, like before, the organization and the billing account. Like before, the next thing we have to do is enable the Compute Engine API. And so we've created a Google Project Services resource that links back to our project and enables specifically the Compute Engine API. Then after that, we can create the instance. This has all of the same fields filled out as you saw in the Cloud Console version, but now it's been Terraformified. Notice also at the end that it depends on that Google Project Services APIs. This is a way for us to tell Terraform that we need the APIs to be finished enabling before we can actually create the instance. At this point, all we need to do is set our variables and run Terraform apply, and the entire environment would be set up. You don't need to wait for each individual resource to finish before manually starting the next one like we did in the Cloud Console. And if we turn this config into a module or edit it in some other way, we can easily scale up or down with the number of users that we need to support. If changes need to be made across the board, then now requires a change in just the one configuration file, rather than having to go through each project manually and do it. Once again, because of the nature of this presentation, I've kept the demo small, but it could easily be expanded to include IAM policies, custom machine images, networks, load balancing, and any of the other resource types that we support in Terraform and Google Cloud Platform. So next up, I'm going to hand it back to Seth, and he's going to run through a live demo with some of this.
All right, thanks, Dana. Just 1 second while I'm getting everything set up, so hang on the line. I had a slight snag, as live demos do, and I need to request a quota increase so that I can actually do the live demo. So give me like 2 seconds, and I will share my screen. All right, folks, while we're trying to get that resolved, I'll go ahead and walk you through some code here. So let me share my screen. Okay. Can everyone see my screen? Cool. All right. So what I want to show first is very similar to what Dana showed, but using some of Terraform's built-in syntaxes to make this a very repeatable process. So the story that I'm trying to build here is, let's say I'm a trainer. I work for a company that provides training. But the training I provide is actually Terraform training. So in order to be able to teach my users about Terraform, I need a way to easily give them cloud access to all the various resources that Terraform can manage, but I don't want them to pay for it. They're already paying to attend my training, and I don't want them to have to sign up for, a Google Cloud account or an Amazon Web Services account or an Azure account. I just want them to show up and do the training. And this is something that I've personally struggled with before. Having written most of the HashiCorp training, and as you know, we make Terraform, so we offer Terraform training. One of the challenges was asking people to sign up for these accounts in advance and having them pay out of pocket to manage these resources. So when Google came to us and said, hey, we have this really cool organizational roll-up billing, it seemed like a perfect fit. So this is the code I'm showing you here is actually a sample of some of the ways that we build virtual training environments for our attendees using Google Cloud Platform. So the first thing we do is every attendee gets their own Google project. And if you remember from Dana's part, the Google project is just your little slice of Google Cloud Platform. And unless explicitly allowed, you can't talk across projects. So the attendee gets full reign. They get what's called editor permission in their project, which allows them to pretty much do everything in the project except delete it and change like billing information and access billing information. So they'll be able to create, read, and update compute instances inside their own project. Because they're not an owner, they won't be able to see my billing ID or our billing information, and that billing actually gets rolled up to our organization. So as an attendee, your only requirement is you must have a Google or Gmail account. So you either need a public Google account or a Google organization account. Even if you've never used Google Cloud before, if you just have a Gmail account, all we need is your Gmail address, and we add you, and it'll automatically create your Google Cloud account for you. And you just go to cloud.google.com, and your VM is sitting right there. Next, I create an IAM policy for each training. And one thing to note is, unlike what you saw in Dana's slides here, I'm using Terraform's built-in count parameter that I've highlighted here on line 12. What the count parameter does is it says create n or more of these projects. So I have a variable called trainees, which I'll show you now, which is just a list of email addresses. So this is my personal Gmail address. So I'm adding myself as a trainee for the purpose of this demo. But for a real training course, this would be a number of different Gmail addresses. So if there are 10 attendees or 10 trainees, then we'll create 10 projects. If there are 2, we'll create 2 projects. One thing to note, and this is a little bit of a gotcha that I always like to point out with Google Cloud Platform, is that when you use the UI, Google Cloud will automatically generate a UUID for your project. When you use the API, you need to generate that yourself. Thankfully, Terraform has built-in support for what's called random ID, which generates a high-entropy random ID. In this case, I'm generating a 4-byte length hex, which is 8 characters. So each trainee will be trainee-something, something that looks like a git SHA, if you will. And again, I'm attaching that to the billing ID and the org ID of the Google project. The attendee won't be able to see that information because they're only an editor, but will be billed for anything that they do. Next, we create an IAM policy that gives me, in this case the trainer, admin or owner permission over all of these projects. That means I'll be able to, say in a remote training, I'll be able to access their project and access their instances and see what they're doing. I can check on their progress, I can see if they're stuck, and I can actually jump on their same instance via the in-browser SSH access and quickly help them out. Next, I'm giving the user editor permission. And as I said, that's going to give them mostly admin access with a few caveats. Notice though that here I hard code my user, but here I use Terraform's interpolation syntax. What this says is give me the trainee at the current count.index. And remember, the trainees is a list of email addresses. So this will actually compile into something like this whenever the code actually runs. But because it's dynamic, all we have to do is add and remove people from the variables.tf file, and all of the policies will automatically get updated. Now, our actual policies include additional restrictions, such as quotas and limits, that don't let the user spin up their own Bitcoin mining ring. But for the purposes of this demo, this is very straightforward. Next, we attach an IAM policy to that trainee with policy data. And the policy data is just what I showed you. We assign that IAM policy to their project. So here we're mapping a project to a policy to a user. Next, we enable a series of services on that project. By default, when you create a project in Google Cloud, it doesn't have any services enabled that we would need to interact with Terraform. So here I'm enabling a few different services, such as the container registry, the compute component, the storage APIs, etc. If I wanted to enable another service, all I have to do is add it to the list. So let's say I wanted to add IAM. I could easily add that, and now the user would be able to manage IAM credentials within their project, so long as their permissions allow that. Again, we're creating one of these for each trainee. So each trainee will have their own instance of Google Project Services, and the project will be tied to their project. And then lastly, and most importantly, we create a Google Compute instance for the trainee. This instance gets launched in the region that we're running in. So in this case, I'm just using the US Central region, but you could localize that wherever you'd want. Enabling IP forwarding. Again, we're creating one of these for each attendee, but we're putting this resource inside that attendee's project. So what that means is that each project belongs to an attendee that they have almost full control over with a pre-built instance. In this case, I'm just launching a standard Debian instance. For actual training, we launch an instance that we've baked with another open source tool, Packer, that has Terraform and Packer and a bunch of other tools pre-installed, as well as things like Vim and Emacs, so that they can easily work in the web UI without even needing an SSH client installed locally. We give them a local SSD. I upload my personal SSH key, so this allows me to SSH into any of the students' instances from my local workstation to be able to help them debug situations and check on their progress. And then lastly, we apply the default networking interface, and we give the instance a public IP. That's what this last line here, the access config that's empty, assigns a public IP for the network interface. So this means that the users would be able to SSH using their own client if they wanted to, but it also means that they can SSH via the web browser. There are three variables. We have a org ID, a billing ID, and trainees. So the org ID is my organization ID. The billing ID is my UUID that I want to bill to. And then, as I said before, the trainees is just the email addresses, and they can be either Gmail or Google G Suite account email addresses of the trainees that are going to attend this. Now, unfortunately, I was hitting some quota rate limits because I tested this one too many times, but we'll try it out, and if I hit the rate limits, I'm sorry, the demo's not that interesting. But if I don't, it's a really cool demo. So let's check it out. So first I'm going to go ahead and run Terraform plan. And what we can see here in this output is that Terraform is going to create the Google Compute instance named trainee, and it fills in all of these attributes for us. So if you remember, there's a can IP forward equals true option. That got filled in for us. There are also some default options like create timeout that we didn't fill in, but Terraform fills those in by default. Here you can see that Terraform actually read my public SSH key from local disk. It's going to be uploading that as metadata. If we scroll down a little bit more, we can see the Google project that we're creating. In this case, we're assigning it a billing account. That billing account came from the variable. The org ID also came from the variable. This project ID, here's those 8 characters that were randomly generated by Terraform for us. So that's going to be the project ID inside Google Cloud Platform. Next, we're creating the bindings for this policy. Notice that in Terraform, if we go back to this slide here, in Terraform we wrote this really nice block of code here that lists two bindings for different members. One is an owner and one is an editor. That actually gets compiled down into this JSON that you see here, and Terraform handles that transparently for us. So we don't have to worry about escaping things or dealing with the actual JSON struct. Terraform just does it for us automatically. But if we look closely, we can see that there's one binding here, or sorry, two bindings here. The first is a role of editor for seth.vargo@gmail.com. The second, which starts here, is a role of owner for seth@sethvargo.com. Now, I happen to be both of those people, but you can imagine a situation in which I wasn't. Next, we create the actual services on the project. So the project gets filled in. That's the same project ID from above. And then we activate all of the services that you saw before. So moment of truth. Let's see if my request went through. If it didn't, it's okay, though. This is why live demos are awesome. What this is doing is Terraform is actually communicating with the Google Cloud APIs right now to try to create this project. And as you can see, I've hit a quota limit. This is why you shouldn't practice your live demo before you do it, I guess. But the quota limits are actually really graceful. I've just done this apparently too many times this morning. So unfortunately, the demo's not going to work, but I will publish the code on GitHub, so you're free to try it out on your own.
Hey,
Again,
Seth, I can run the demo.
Oh, okay, cool. We'll switch back to Dana, who will run the demo.
Hey, everyone. So, while Seth was explaining all of this to you, I started running it myself. And so you can see right here that it's actually creating these Google Project Services resources, which are the ones that enable the APIs. I set 3 different trainees in mind, so it's doing it 3 different times at 0, 1, and 2. If I scroll back up, we can see that was for me at my Gmail, as well as Seth and Seth's Gmail somewhere up here. I don't have very good colors. Oh, there it is. Oh no, apparently oh, okay, sorry. I'm using an outdated version of Seth's. This is super exciting. Let's try again. You should always run plan before you run apply, by the way. No. Okay, never mind. I can't run the demo. I'm sorry, Seth. I tried.
It's okay, you got further than me. And this just goes to show you that even experts who work with these tools every day still encounter errors every now and then. And it's okay, we work through it. Unfortunately, this is going to conclude our webinar today. I know there were some really great questions, but unfortunately, we're right at the top of the hour. So I'm going to hand it over to Amanda to close this. But as I said before, Dana and I will work to publish these on GitHub, so you'll be able to try these out. Just don't try it too many times, because you might get rate limited. Amanda, I'll hand it over to you.
Thanks, Seth. Thank you, everyone, for joining us for today's webinar, and thank you, Seth and Dana, for presenting. As we said at the beginning, this webinar was recorded, and we will make the recording available after processing. We will also send an email to everyone who registered for the webinar, the complete list of questions and answers after we summarize all that data. Thank you so much for joining, and have a great day.